Hello everyone, today we'll be talking about recursion. The photo in the slide represents recursion. It's a guy holding a mirror, and if you look in the mirror, it's the same guy holding the mirror, and if you look in the mirror in that photo, the mirror is within the mirror, it's the same guy holding the mirror. Same image. The same image keeps happening when you look in the mirror. And this is a perfect representation of recursion. So what is recursion basically? Recursion is just a function that calls itself and is pushed in the stack in memory. And a stack is a data structure is whatever the first element that's put in is the first element that's pushed out. Whatever the first element that's pushed in is the first element that's pushed out. Popped, or you can say popped out. People think recursion is this fancy thing where it is something is happening magically in memory. No, it's just the function calling itself and being called in the stack in memory. We're going to go over through this lecture, we're going to go over recursion and simplify it for you. So I took the notes from this book. I read a book on recursion, and my goal for today is to simplify and make recursion very easy for you guys to understand. All right, a perfect analogy for recursion is from the movie Inception. The concept of dreams within dreams. Right? So, I'm going to give you a brief description of the movie Inception. It's about basically Leonardo DiCaprio has a dream machine. In that dream machine, it allows him to go into dreams. And once he's in a dream, he can use that dream machine to go into another dream. And then in that other dream, he can use that machine to go into another dream. And this is the illustration of see what the stick figures is the illustration of Inception right here. And you could apply the concept of dreams in a dream with the same functions within functions, function calls of the same function. All right, the three laws to recursion is a recursive algorithm must call itself recursively. A recursive algorithm must have a base case, and a recursive algorithm must change its state and move towards that base case. So basically, what is a base case? We were talking in the previous slide about Inception. Basically, the base case is exiting from the dream and going back into reality. But another way to simply put it is it's similar to the end statement of a loop iteratively. Again, it's similar to the end statement of a loop. So we have two pieces of code below. One is an iterative approach to count to 9, and one's recursive approach to count to 9. As you can see, both have, from the loop, it says, if you look at the loop, if you have the loop statement, you can see it's counting to 10, and stop the loop at 10. In the recursive solution, you can see that if once it reaches 10, exit from the recursive statement. And both of these approaches produce the same result. Again, another way to think of base case is think of it as the same statement as ending a for loop. So if your goal, we look at the for loop, the goal is once you reach 10, exit the for loop. You look at the recursive solution, once it equals 10, exit the recursive statement. Pop the stack. So I got this image from XZD, a place that makes like programming humor comics. And so we have a problem here. We have to look for our keys. So we make a pile of boxes to look through. If we find a box, we add it. So this is our iterative statements, I plus 1. Now, both, and the recursive one is, we find a box, go through every item in the box as a recursive function. If you find it, you find a box, keep making a recursive call. Keep calling yourself. If you find a box. But if you find the key, exit. If you find the key, exit. You're done. Both have the same statement / base case to exit the calls. All right. So I coded a recursive function called recursive inception function from the movie Inception. Okay, so right here, you go into a dream, and then you're Leonardo DiCaprio, and you go dream 6 here. So then dream 6 gets pushed to the bottom of the stack. Dream 5, you get pushed to the bottom of the stack. You're still in the dream. You're still in the dream. Dream 3, you're still in the dream. Dream 2, you're still in the dream. And you have to reach to dream 0 to go back to reality. So keep going in dream. You're in a dream. And then once you reach dream 0, the dream 0 function call here, you wake up and you're back in reality. Leonardo DiCaprio wakes up. I'm back to normal. I'm back in reality. I'm no longer in the dream. And this function you see is a tail recursive call. All right, as you can see. Oh, okay. When looking at this code here, you can see that when you probably see it better here, we're following the laws. So law 1, recursive algorithm must call itself. Law 2, in that we're moving towards our base case, so n-1, so eventually we're going to reach n equals 0. We're moving it, and a recursive must call algorithm must have a base case, and we do have our base case. This is our base case, so we can see the 3 laws here. Where were we? Oh, we're at the function. Okay. So I'm going to clear Inception, and you see dream 6, dream 5, dream 4, or dream 3, dream 2, dream 1, and you woke up and the dream is over. Yay! All right. Let's go back to where we were. Okay, types of recursion. So you have tail recursion. The function I just showed you, the inception function, is tail recursion. You have a head recursion, so it gets executed after. So the recursive call statement is before the code. A tree recursion, so if you see more than one recursive call in a function, by default that will be a tree recursion. It's going to cause it to be a tree. Nested recursion, so it's a function that calls itself in the function's parameters. And indirect recursion. Indirect recursion is basically you have 2 functions, and let's say you have function A and function B. Function A and function A is calling function B, and function B is calling function A recursively. So nested recursion and indirect recursion are not really important. You're not going to see them that much programming or asked probably in an interview question. Mostly you're going to see tail recursion and tree recursion and head recursion. Or you're going to see a mixture of tail recursion and tree recursion. Again, you're going to see a mixture of tail recursion and tree recursion and head recursion. You're going to see most interview questions or practical applications using recursion will have a mixture of 1, 2, and 3. So what is tail recursion? Basically, it is the code is getting executed before it's being pushed into the stack. The code is getting executed before it's being pushed into the stack. So in tail recursion, you have tail 1 gets called, gets pushed into the stack here. And then we follow step 2. Tail 2 gets called. Tail 1 gets called. We execute the code. It gets pushed in the stack. Tail 2 gets called. We execute the code, and it's now pushed into the stack. Tail 3 gets called, we execute the code, it gets pushed in the stack. Tail 4 gets called, we execute the code and gets pushed in the stack. Tail 5 gets called, we execute the code, we push in the stack. Tail 6 gets called, we execute the code, and it's pushed in the stack. Until 7, we reach our base case. Once we reach our base case, tail 7 pops off from the stack, tail 6 pops off from the stack, tail 5 pops, tail 4, tail 3, and tail 2, and tail 1 pops, until we have nothing in the stack. Just remember, alright, so let's execute our tail function. Where's our tail function here? Oh, and it goes 1, 2, 3, 4, 5, 6. Count 1, count 2, 3, 5. And then when once it reaches count 7, everything gets pushed off the stack. So head recursion is basically the opposite of tail recursion. We push to the stack first. Once all items are put, all function calls are pushed into the stack, we pop it. Head 7, you look here, is our base case. So this gives us, okay, we're done. Pop everything from the stack. So head 6, it outputs count 6. And then head 5 outputs count 5. You can see in orderly. Count 4. Head 4 outputs count 4. Head 3, once it's popped up, after you pop head 4, head 3 once it pops off, count 3, count 2, count 1, until you have no more function calls in the stack. It is the opposite. So anything executed, it will execute the code below the recursive call. And this, once it's in the stack, the code is still in memory, or you could say still in state. So once you pop it off the stack, it's going to, from the bottom left where it was initially, so it's going to say, okay, I was over here. Okay, let's do, sorry about that. So we were over here, right? And it says, okay, we have to execute the rest of the code. So it stays in, so once in stack, it stays in state. Once it's popped, it has to execute everything below the recursive call, and then it is eliminated from stack. Let's execute head 1. Let's execute head. Let's the head function here. As you can see over here, this is tail and this is head right over here. You can see that it is backwards. It's calling from the bottom. Sorry, it's calling from the top of the stack until all the function calls are eliminated. All right, you have indirect recursion. This is not really important, but it's basically a function call. So it's basically, you have two functions. You're calling function A, you're calling function B, and function B, you're calling function A. Hold up, let me just quickly modify that. That is wrong. Sorry, function A. Just gonna modify this really quick. here. Sorry about that. So you can see here function A in direct recursion, function A is calling function B and function B is calling function A. So if you look at this code here, you see, oh, it calls function A, and then function A is then calling function B. Function B is calling function A, and it keeps repeating itself until both functions reach their base case. So let's, okay, func B, okay, let's execute this. As you can see, here we have the same output, 20, 19, 10, 8, 4, 3, 2. So it calls, where's that 5 here? So basically, indirect recursion is basically just function calling itself recursively in a circular manner. You will hardly see this in like real world applications or interview questions, but it's just good for you guys to know. Nested recursion is basically a function calling itself in its parameters. We have our nested recursion here. You can see an 11. So we're going to do a quick trace. So if you put F95 plus 11, this equals 96, but this is inside. You see fun 106 is in the parameters, and you keeps execute, and then from function fun 17 97, you can see fun 107 is in its parameters, but then it calls its main, it goes to the main function, the main one that's not in the parameters, fun 97, and then fun 108 equals fun, this is in the parameters, execute fun 98, fun 109, it has outputs 999, 99, and fun 109 in its parameters. Okay, then it goes from fun 99, keeps going, and then fun 110, 100, it outputs 100, but in its parameters is 110. So, and then fun 100, and then from fun 111, fun 101, and then from fun 101, so until both calls are greater than 100, it will end. That's the base case. Until both functions within functions are until 100, the recursive function will end. Again, nested recursion, hardly see this in real world applications or in interview questions. It's good. It's just good to know. You'll hardly see this. Okay, tree recursion. This is the most important recursion you're going to know. You're going to see this recursion in most algorithms. You're going to see this in most recursive algorithms, most interview questions, and most real-world applications. So you're going to see this like in divide and conquer and backtracking. All right. For tree recursion, we're actually going to break it down. So we're going to go to open board. I'm going to actually sketch this one out. We're going to do a walkthrough. This is the most important one out of all of them, is tree recursion. Out of all the recursions, tree recursion is the most important one. We're going to do a walkthrough through this one. I need my pen. All right. Hold up. Sorry about this. Can I copy? Okay. Open board. Actually, we'll take this tree recursion function here. I'm just going to copy and paste it. Okay, we have our function here. And we're just going to call it function. We'll just call it fun. All right. And then the parameters for fun will be, this will be here. Fun 3. All right. We're going to break this down recursively. Okay. So you have fun 3. We're going to code our stack here. Should not. Just quickly break this down for you guys. Oh, let me just quickly edit this quick. Okay, here. So let's break down this recursively. So what's happening here? So how you break, so you have fun 3. Okay. Let's have our output. All right, we output 3. 3 is greater than 0. Yeah, that's true. 3, okay. Then we go through this statement here. Fun 2. Okay. And then do another recursive call until we exit. Fun 1 until we reach our base case. Fun 0. All right. So you go back here. So we have 3, 1. Again, this tree recursion is a tail recursion at the same. This is both a tail and a tree recursion function. And 0. All right. And then I'm going to come here. Oh, sorry. If it's 0, don't print. Sorry about that. Sorry. This goes null. Okay. Then 1 here. 0. exits its base case. Okay, exits case. Then you have fun1. All right, 3, 1. And then you have fun 0. You go back here, then you have 0 again. We go back here. All right. Sorry. Okay, we have our function here. Now we're going to recursively walk through it. We're going to do a code walkthrough. So here is in our main. In our main, we're going to put 3 as our value. We're going to do a code walkthrough. So let's do a code walkthrough here. So we have fun 3. Okay. And then here you have your output 3, prints 3. Then you have right here executes fun 2. You go back, you call the recursive function again, 3, 2. Fun 1. 1 calls itself. Okay, fun 0. Done. You exit the base case, exit the recursive call here, exit, and then you go to 2, fun 1, print 1. Again, this repeats itself. Exits the base case. Now we go to 2. Print 2 again. Okay, we're running out of space, so we'll just go here. And then fun 1, 1. Fun 0. Go through the recursive call again. All right. And here is to summarize. This summarizes our recursive call. And we did a walkthrough here for our tree recursion. So the output is 3, 2, 1, 1, 2, 1. Let me just let's get a screen. Hold up. Let me just get a screenshot. Can I get screenshots? No. 2, 2, 1. All right, we're going to do a recursive track here. We're going to do a recursive walkthrough. So, all right, we're going to do it in open board. Hold up, let me just copy and paste the function here. Get the Python function. Let me bring it into, let's get open board. And we're going to instead call this fun. Let's change this to white because the green makes it look like it's commented. And change this one here to fun, to fun, to fun. All right, let's do a recursive walkthrough. Right here will be your output. So here, fun 3. Okay, outputs 3, 2. I'm gonna track recursive 1. The function calls itself again, 0, 0. Go back here. 1 again. 0. When fun is 0, it exits the recursive call. So you could say right here we did let's exit. All right. Fun 2. Now print 2. It's going to be similar to the recursive call on the left tree. All right, we don't have no space here. We're just going to do it here. Fun 1, 0, exit, 0, exit. We do the same thing here. Fun 1, prints 1. So 3, 2, 2, 1, 1, 2. This is our output, and we just did a code walkthrough on a recursive tree function. We're going to do more walkthroughs on recursive tree functions. This is just a simple one. Also, take note that this function's also a recursive. This is also a tree recursive function and tail recursive function because the function statement is being called at the end of the function. All right, and we go back to our. We go back to our slides. All right. As you can see, we have a similar output. And let's actually run. But instead, this is called func tree. Let's actually run our recursive tree function. All right, let's comment the func A. Yeah, and this is the output for the recursive tree function. All right, thank you for watching. Again, it's really important if you to understand tree recursion, head recursion, and tail recursion. I'm going to do a part 2 on this. In part 2, we're going to do the Fibonacci sequence. We're going to talk about backtrack, what types of algorithms that are that use tree recursion, head recursion, tail recursion, like mostly tree recursion. We're going to talk about divide and conquer, backtracking, and memoization, and when to use recursion and when not to use recursion. All right, thank you for watching, and I hope you guys have a great day. Okay.